This presentation will walk through calculating runoff for earthworks, and we'll look at it in two parts. The first part is going to be focused on calculating storage volumes. Part two is going to focus on calculating the flow or the discharge out of a watershed. Our first step is to determine the drainage area that is flowing to our pond, and we'll take a pond in a real-world situation. This pond is located here, and it's located in a subbasin of a larger watershed. So our subbasin is bounded by ridges along either side and the top here. So in order to figure out our drainage area, we need to trace a line along the ridge, and this will establish a polygon that represents our drainage. Now, water flows always perpendicular to contour. So we can imagine little arrows coming perpendicular off of all of these contour lines, flowing down towards this point. And it arcs here as the last bit of water moving perpendicular to this pond location. So that's our total area. We need to calculate this area in square meters. We can do that in a number of ways. One way is to put an overlay grid on top of this map and visually calculate it. But we can also use online calculators. There's a series of calculators online that work worldwide to calculate in either square footage or square meters. The next step is to collect the soils data for the drainage area. Now, this information is derived, in this case, from the U.S. Department of Agriculture's soil survey. It's an online tool. And you can draw an area that you want to derive soils data for. So this rectangle captures the entire area of the drainage basin of our pond, which is located here. And it'll pop up information about the soils within this area. So what we're looking for is our soils type. We're also looking for the percent slope of the soils in our area. The next set of data that we want to collect from the soil survey is our hydrologic soil group. Now, these are ratings A through C, and they speak to the rate of water infiltration from different types of soils, with A being the fastest rates of water infiltration, to C being the slowest. So it goes from fast to moderate to slow to very slow. And you can see that the soils in our area are rated C and D. So this would mean that the water is going to infiltrate very slowly. The soils are very likely clay types with less sand and silt. There may also be a non-porous layer like bedrock close to the surface or a compacted clay layer. That would be usually for C, and D may be that we even have wetland type conditions in our soils. But in both cases, the runoff is high. So this table summarizes the soils information that's relevant for our process. And you can see we have 4 types. Now, the first 11D is Belpine Silty Clay Loam. It has 12 to 20% slopes, and the hydrologic soil rating is C. We have another Belpine Silty Clay Loam. What differentiates it is the percent slope, 20 to 30, rating C. 43E is Dixonville Complex with 12 to 35% slopes with a rating of D. And 113C is Rittner Cobley Silty Clay Loam with 2 to 12% slopes with a rating of C. So our third step is to map these soil areas onto our drainage basin. So we have 11E and 11D here, and then we have 43E, the Dixonville Phyllomath Hazel Air Complex, cruising through the main drainage. And we have this little section of Rittner over on the right side here, 113C. We need to determine the area of each of these soils in square feet or meters squared. We can return to our process for calculating that either online or by hand. The other set of information that we need to map onto this as well is the land use. Now, the land use is going to be another factor that we use to determine our runoff coefficients in the following step. In this case, we have an entirely forested land use. But in some scenarios, you may have a few types of land uses. You may have pasture or agriculture, and you may have more upland forest, or you may have a parking lot or exposed bedrock or a road coming through. And all of these different land uses have different runoff qualities. And so we need to understand the square footage of our different land uses as well. We need to also represent that in a map and calculate the area. So we have here clarified this as forested land use. So we can now plot this area into a spreadsheet, and you can see we've represented the soils of the catchment area, and we have the area in acres, hectares, square feet, and square meters plotted out for each of these soil types. We can get an area for each type as well as an area for the entire basin. Our next step is to determine the runoff coefficient. The runoff coefficient is used to calibrate the true runoff volumes from the watershed. And it's calculated taking into account hydrologic soil group, the percent slope, and the type of land use. In order to get our runoff coefficient, we've plotted the average percent slope of all of our soils and our hydrologic soil group. And we can look at our table and find, based on percent land use and the soil group, a coefficient number for each of our soils. So we've entered that number here, and we'll use this coefficient to calculate our total flow volumes from our drainage area. We can use this data to now calculate our total water volumes. So to determine the total water volume, we multiply each runoff coefficient area by the amount of rainfall in inches or millimeters. We then multiply that number by 0.623 in order to convert to gallons. That is the quantity of water in gallons, 1 inch deep in 1 square foot of space. We can convert to liters by multiplying this number in gallons by 3.785. We then multiply this product by the runoff coefficient, and the total water collection potential is the sum of all unique water coefficient areas. So we have our areas here, and we can multiply the area by the amount of rainfall. In order to get gallons, we multiply that product by 0.623, and to convert to liters, we multiply this number by 3.785. In order to determine our total collected water, we multiply annual rainfall in gallons or liters by our runoff coefficient. And that gives us the sum of the collected water from each of these soil types with their own unique runoff coefficients is here. Here's an example of how we can apply these numbers. For calculating storage capacity, we can use this formula to determine the total capacity of our pond to hold water. So with this formula, Vs is the natural storage volume in the dam. K is the selected coefficient of the gully cross-section, and we can see this image here showing these different coefficient types depending on the shape and size of the gully. W is the width of water across the dam wall. D is the depth of water at the dam. And L is the length of the longest stretch of surface. So if you have these numbers, you can determine how much volume your pond can hold. And you can compare that to the total volumes projected to be coming out of your watershed. You can then determine if your pond is adequately sized, it's undersized or oversized to your watershed yields, and how much more water you'll be passing through after you fill your storage. Now we will determine the discharge of water from this watershed. So discharge or flow refers to the amount of water volume carried through a watershed over time. And it's commonly expressed in units of cubic feet per second or liters per second. We can use the flow volume formula to calculate our discharge. So Q equals the quantity of flow in cubic feet or meters per second. C is the runoff coefficient multiplied by I, the average rainfall intensity, for the selected frequency in inches or millimeters per hour, times A, the area of the watershed in acres or hectares. To apply this formula, we already have our runoff coefficient, and we also have the area of the watershed, but we need to determine our intensity of rainfall. So rainfall intensity is the rate of rainfall, and it's the rate of rainfall over a certain period of time. This is one of the more difficult sets of data to collect for this exercise. But in the United States, NOAA maintains precipitation frequency data, and you can pull this data up from the Precipitation Frequency Data Center for your area. Here's an example of the precipitation intensity for this pond location in a 6-hour event, a 24-hour event, in both a 2-year or a 100-year storm. So returning to our spreadsheet, we can plot this data. Here in this row are our intensity numbers in inches per hour and millimeters per hour for a 6-hour and 24-hour event in a 2-year and a 100-year storm event. We multiply intensity by the runoff coefficient and the area to get our flow rates. And then we can sum the different areas to come up with the total flow volume. So an example of applying our flow volumes, we can use flow volumes to calculate the size of our spillway. So on the image on the left shows a chart that helps us calculate spillway width for calculated flood flows. So in meters cubed per second, here's our flood flow. And that shows us what our width should be in meters, as well as our outlet width, depending on our percent slope. This is for really large dams, and a quicker calculation that's been developed by KB Yeomans is to take the square root of the catchment area in acres and multiply that by 4. And the metric formula is just the square root of the catchment area multiplied by hectares. So this presentation has shown how to calculate the amount of water coming off of a given watershed and how that water can be anticipated to provide certain amounts of water volume for pond storage, how large our ponds can be built in order to hold that given volume, and ultimately how much water we'll have on hand in order to supply our farms and homes and landscapes. With the flow information, the discharge information, we're able to also anticipate the rate of water flow through the drainage and therefore water into and out of the pond, and calculate the necessary sizes of our pond outlets, including our spillway. So thank you for sticking with me in this presentation, and good luck with your water projects.